Laws of Logs, Part 1. We have already come across this conversion from exponential to log form. Graphically, the red curve is the exponential curve, which has a horizontal asymptote here. When the exponential curve is reflected in the line y equals x, we get the log graph here. This is the inverse function, and the log graph has a vertical asymptote here, and our line here is the line y equals x. Any graph reflected in the line y equals x gives rise to the inverse function. So a special case first. We have the log of a to the base a. So these two are the same. This always gives 1. So the log of 2 to the base 2 is equal to 1. If I write this in its exponential form, we get base power. So 2 to the power of 1 is equal to, and I haven't used that 2, that goes here, 2 to the power of 1 is equal to 2. Another special case is the log of 1 to any base is always 0. So the log of 1 to the base 5 is 0. Again, base power, so I'm going to write this in its exponential form. Base power is equal to whatever's left here, 1. Anything to the power of 0 is 1. Another reason why log 1 is 0 here on the graph, x equals 1, so we have log, doesn't matter what the base is, any base of 1. And what's the y coordinate? Right there on the graph, it's 0. So log 1 is 0 just by looking at the graph. Another thing with the log graph, because there's an asymptote here, we know that the values of x have to be greater than 0. So you can't have the log of 0, there's no graph when x equals 0, there's an asymptote, and we can't have the log of any negative number either, there's no graph on this side. The power rule for logs states that the power k can move to the front and multiply with the log term, like this. Or we can use this the other way around. If you have a coefficient in front of a log term, you can move the power back up here, like this, to get rid of the coefficient in front, which will be useful when we look at some of the other laws of logs. So in this example, I've got the log of 5 squared to the base 3, so I can move that power to the front here. So I can write that as 2 times log 5 to the base 3, or I can put the power here and it's log 5 squared to the base 3. In this example, starting on the left, I'm writing the 16 as 2 to the power of 4, then I move the power of 4 to the front, like this, and we know that the log of something to the same base is equal to 1, that's 4 times 1, which is 4. In this example, starting on the left, we've got a half as a coefficient. If I bring the half up and I write it there as a power, like this, 36 to the power of a half, or the square root of 36, is 6. In this example, 1 over x can be written as x to the power of minus 1. That power of minus 1 can move to the front, like this. Instead of writing minus 1, we can just put a minus. The base is missing, so base 10 is being used. In this example, that base, the base is 2, the power here cannot move to the front. I can't do this. And that's because that power of 2 is only on the x, it's not on the 16. However, if if I write a fully squared term like this, now that power of 2 can move to the front, so I've got log 4x to the base 2, all of that is multiplied by 2. The multiplication law for logs, so we have log x plus log y, and we can write this as log and then the product of x and y. Now this term is positive and this term is positive, so whatever you see here and here, you multiply them together like this. So log 6 plus log 3 is equal to log, we've got the same base throughout, both of these are positive log terms, there's no coefficient in front of each, so I can multiply the 6 with the 3, so log 18. Or I can do this in reverse order, log 18 is equal to log, let's say if I pick 9 times 2 this time, 9 times 2 for 18, so that's log 9 plus log 2. I've used base 10. In this example, I need to get rid of the coefficient here in front of this term and move that up here using the power rule, and then I've got log, same base throughout, it's base 2, so it's 4 to the power of 3 times 4 times 3, which simplifies to 768. In this example, I'm using base 10, no coefficient here, positive log term, so I can combine them both. I need to multiply the 2 plus x with the a minus 8, so I can write it like this, 2 plus x, a minus 8. The division rule for logs, so we have a positive log term, so the x goes in the numerator. That's a negative log term, so the y goes in the denominator. So log 10 is a positive log term, no coefficients there, the 10 goes into the numerator, minus negative log term, so whatever's here will go into the denominator. Same base throughout. In this example, we have an x squared times y, and I have a single log term, and I'm going to split this up as log x squared plus log y. This is just from the x squared and the y in the numerator. Moving on to the denominator, all the terms that I get for logs for the denominator will be negative, but there's only one, it's minus log z. So log 1 over x can be written as log 1 minus log x, and log 1 is 0, so we're left with minus log x. And here we have a single log term, we have a fraction, so in the numerator we have a 10, log 10. We have an a plus log a, we have a b plus log b. In the denominator we have c, so that's minus log c, and we have d, which is minus log d. And we know that the base is 10 because it's not written, so this term, log 10 to the base 10, is actually 1. A list of all the rules of logs which need to be memorized.